The next speaker is very difficult to introduce for me because it's my wife, Erika Eiser. But the consequence is that I didn't have to ask her about her CV because I roughly know, at least I hope I do. And Erika studied in Constance as an undergraduate, then was left for masters to work with Jacob Line, and actually by doing so freed up a PhD position for a subsequent student. And maybe she should have stayed in Constance because the next student was called Gert Schoen, and he went to Bell Lab to progress to great infamy. But anyway, Erika went to Jacob Line, then she went to Montpellier, Grenoble, Amsterdam, Cambridge, and now she's joined Cambridge and Trondheim. And I will take no more of her time because that would create problems for me later on. And Erika is going to talk about optofluidic crystallization of colloids tethered at interfaces.
Thanks, Dan. It's a wonderful pleasure to be here, and especially after quite a long time not being able to travel to nice conferences and meet and talk to all my colleagues, which is always such a great pleasure. And already today, in less than a day, I made new friends, which is great. So I'm really happy to be here, and very grateful also to Tony to think of me occasionally. So I'm going to present some work that I had essentially done back in Cambridge, but some of the work is ongoing, and I still have some PhD students working on that. But let me start right away, not to take too much of your time. The idea what I'm going to present is we developed a system of creating a large, very large oil droplet onto which we can attach through DNA very accurately colloid particles, and therefore create a two-dimensional crystal or two-dimensional system of colloids. So this is this animation here is not an animation; it's actually a simulation, molecular dynamics simulation that represents our real system. And what I'm going to talk about is how can we modify these colloids just using light. And what can we do with such a thing? Okay, now why are colloids interesting at interfaces? There has been a lot of work done, especially also by the group of Bernie Binks on colloids at interfaces. The important thing is colloids, if they are partially wetting both water and oil, can act like surfactants. Only when you add these colloids at the interface, the energy they have is so much larger than a small surfactant molecule. And some beautiful work that has been done by Paul Clagg's group is taking a system where you have you prepare it in the one-phase region, you add colloids to it, and then you quench it into the region where the two phases phase separate. The colloids will go into this interface and create or sort of settle this porous bicontinuous network, which has quite interesting applications, I think. Other people worked a lot with colloids at interfaces by placing them here, for instance, air and oil or water. And when they are charged, you can play with the interactions between the colloids continuously by changing either the salinity and therefore the Coulomb interactions, pushing them apart, but also using the deformation of that interface, which is elastically quite intense, and that can lead to self-assembly of colloids at these interfaces. I think Kathleen Stevie did some really beautiful work, not only just with spherical colloids, but little rods, and showed how they, due to the deformation of interfaces, they will start to self-assemble into long chains. Now, we started and decided to work differently, and we wanted to have colloids at an interface, but not in the interface. And the way we do that is by taking a very large oil droplet that we produce in a microfluidic device. It's silicon oil with very high viscosity, and we can stabilize it with surfactants, here SDS, and onto this we can attach DNA. Here I have a little double-stranded strand and a single strand, which provides the high specificity of attaching our colloids to that interface. I explain in a moment why we use the double strands as well. Now, in solution, then, we can bring in colloids that have a similar setup, but they carry the complementary DNA part, so we can directly attach reversibly these colloids to this interface, because double-stranded DNA only is held together by hydrogen bonds. So if I heat it up, it comes off, I cool it down, it sticks again. So it's highly reversible. But the most important why we chose this oil droplets is that once they're attached, they're still mobile. They're still able to float on that oil-water interface without deforming the interface itself. So we have, as I mentioned, it's important to remember what type of interactions we have. So the DNA interactions are really super short-ranged, because only when they meet enough of a few nanometers, then they start to feel each other and bind. So the attractive force, it can be very steep, but the attractive force is only on a range of a few nanometers, up to 10, 20 nanometers. We have used the double strands simply because they're inactive, but they prevent van der Waals interactions between the colloid and the oil droplet. So we screen van der Waals attraction, non-specific, and we add salt. DNA is negatively charged in water. If you add a bit of salt, then you screen the Coulomb repulsion. And as a consequence, you have now created colloids that can diffuse on that interface freely, but they behave like hard spheres. There's no other interaction except that when they bump into each other, they repel. So this is very important. No attraction between colloids on the interface. So this is a view from below. So what we look at is so to speak, the south pole of our oil droplet, because the oil droplets move up due to buoyancy. So what we can do is this is a bright field micrograph. It looks a bit unclear outside. It's simply our focal depth is not deep enough to represent and to view all colloids, the entire oil droplet at the same time. So we only focus on this southern part here. I call it southern part. It could be also northern part if you wish. Okay. Now the important thing is we do particle tracking. Here's a real image of a colloid tracked during its thermal motion on that interface. And we also verify that really they do diffuse freely on our interface. But they are attached. And that's the really important part. And that will become also very important for later on to understand what we are seeing. Okay. So once we addressed all these things and we built our system, we ask ourselves what happens when we introduce an optical trap at the interface. Because we wanted to trap a particle and see, can we move these particles at will with our optical tweezers? Now, before we go to that, I just very quickly for everybody, especially the young people watching these lectures, to remind you what is an optical tweezer. When you take a laser light and you focus it into a very narrow focal spot, then you create basically a harmonic spring for these particles. So the particles experience photons, and you have a Gaussian beam in the middle, and when it moves away, it's the scattering forces that push the particles back in. If you have several particles in your optical tweezers, then, so if the focus is not really narrow but wide, then what you have is you start to, so these are dielectric materials. If you move in with polarized light, you set up a polarization field in the colloid, and that gives rise to scattering, and these scattering forces induce an attraction in plane in here. And I will show you also later pictures of that. So people have looked at that. So you can, for instance, with a large laser beam, push colloids directly onto an interface. Here, this is on a hard interface. And they start, because of all these interactions, the optical scattering interactions, they start to aggregate into a 2D crystal. Now, the interesting thing is, this was on hard surfaces. We are working here on liquid interfaces. Okay, so our system is such that we have here some laser. We used 1064 nanometer laser, an acousto-optical device that is just helping you to steer the beam, and you can trap up to 50 particles with a single beam. And I don't go into detail here, but what you can do is we can really very carefully place our focus at that interface, trapping only a single colloid. How do I know that I do trapping of a single colloid? This movie shows you in bulk, not when I switch on the trap, particles get stuck, then they are released. Now I moved it with the AOD around, so I can really manipulate my particles at will in our system. Now, what happens when we now trap a single particle at that interface? And we know that we trap a single particle because the laser, the sort of harmonic potential that holds this particle in there is proportional to the intensity of the laser we use. And we see that the width here is something like 500 nanometers, or up to a micron, which is the size of our colloid. Now, so we really make sure we don't trap 2, 3, or many more particles. It's only a single colloid that we trap. Okay. And now I would like you to look at this red spot. That's inside that red spot is my optical trap. Now I switched it on, and you see all of a sudden particles come streaming in and form a crystal. Now when I release it, they start to diffuse freely again. And that also shows you that they are really hard spheres. They are not interacting due to any non-specific interactions here. And this is highly reproducible. You switch on, you switch off, you on, off. It comes in and out, and we can see all sorts of interesting things happening. Now, just why do I show you some of these snapshots from this movie is, so when we switch on the trap at this point, indicated by the red dot, you see that those particles very close by very rapidly move in. Then you still have a depletion, but then slowly, even particles that are very far away, like several colloid diameters, are pushed towards the center. And that is they can feel the trap, well, not the trap, but the effect of that, even 20 colloid diameters away. So this is something that puzzled us. And it took us over 1.5 years with some very good hydrodynamicist theoretician helping us to understand what is happening. And this is something that we really took a long time. The experiments were done rather quickly, but the interpretation took us a long time. So we have 3 important observations. That is, when the trap is activated, we see crystallization. Now remember, crystallization, the way we know it is actually an equilibrium phenomenon. But this is a highly out of equilibrium process because we keep pumping light energy into the single particle that we trap. And our aggregates are way larger than the trapping region, which is also very strange. We only have attraction, trapping only one particle, and there's no further attraction due to the laser focus. And we see this very long-ranged attraction here, which can be several colloid diameters. Now, one thing I also was puzzling in the beginning is, I don't know whether you have ever made this experiment, but when you heat something, then usually things move away from the heat source to the colder places. And that's also for colloids. Usually when you heat them, if there's anywhere a colder place elsewhere in the sample, it will move in there. And actually I will show you in a moment that we indeed measured the Soré coefficient, so that it tells us whether a colloid will move to the cold or to the hot anode or hot place in the presence of a temperature gradient. But so what you would expect is that if you heat it, and that's what happens when we trap the particle, we locally heat it just slightly, like 5 centigrade above the bulk temperature. And as a consequence, you would expect that you have a Marangoni effect that pushes particles away from that hotspot. We calculated all the numbers and we looked at the Marangoni number, and what we observe or what we estimate from the material constants in our system is that effectively we expect all the molecules to move away from the hotspot with an enormous speed, 1 meter per second. That's amazing, you know. But instead, what we observe from tracking the particles coming in, we see an average velocity of the colloids on the interface of minus 100 micrometer per second inwards to the hotspot. So this is this kept us. Oh dear, I have here some funny signs. I hope you forgive me. Okay, so we know that if we have a more complex behavior, we could possibly, due to the presence of the surfactants, induce a flow towards the hotspot, but we had no success in finding anything in the literature that explains what we see, that it should actually go in outwards. As I said, we measured the thermophoresis and the Soré coefficient on our colloids for all exactly the same colloids with DNA coating or with other coating or just no coating. They all always go to the cold side in the sample. Okay, so here comes in the collaboration I developed with colleagues at DAMT in Cambridge and Ronald Joy Adhikari and his postdoc then Rajesh Singh. And they are really great scientists. Were very enthusiastic about trying to explain what is happening. So as I said, we have a colloid and we weakly heat it. Now if we have just already 5 centigrade increase in temperature locally, this heat decays to the bulk temperature over 50 micrometer. And that's really quite interesting. But normally what you would expect is it would be propelled away from the surface because of that. But because we have the DNA strand, they are like little balloons attached to that interface. You can have wind blowing, they're there, but they can't escape into the sky or here into the bulk. And that is exactly what is happening The second very important part, which for many people may be interesting, is water has a different heat conductivity than oil. So the oil appears colder than the water above. And it is this solving the equation of the conservation of heat, mass, and momentum, and iterating that through, taking into account all the boundary conditions here, we were able to show that it is a combination of thermophoretic force that pulls the particle toward the cold oil phase, and then you have the elastic spring that is compressed, the entropic spring of the polymer that pushes it back, and this constant heating makes it, you need to conduct the heat away, and that's the only way is to suck in water from far away. So you get a convection roll towards the hot spot just because of the presence of this little DNA spring here. And this is really important to remember. If it wouldn't be there, it wouldn't happen. So I don't go through the exact theory, but we showed that eventually that the velocity of the particles being drawn towards the center is basically scaling with 1 over r, the distance to the hotspot. Okay, we show that, so the force is, the hydrodynamic force is 1 over r to the minus 2, and our velocity scales as this. Remember that for Marangoni effects, we have different, it's still there, the Marangoni effect, but it decays much faster than these hydrodynamic forces pulling in the other colloids into the interface. So this is just expressed here. The optofluidic force that we define pushes the particles towards it, towards the hotspot with a scaling with 1 over r squared, whereas the Marangoni effects or forces scale with 1 over r to the power 3, and that is much, so they fall off much faster. Now, I puzzled very often for a long time how to show that you really have actually generated a convective flow towards the hotspot. How do you see that? And when I went frame by frame through all these movies, I realized you can see that very clearly. So when a particle is in focus, the way we define it here, you see it very clearly as a bright spot. And now look at, for instance, this particle that seems to be attached to the interface. And you see that it slowly comes closer and closer and closer, and then it's gone. And the reason why it's gone, when it's moving up, because of the flow field going up, it's so quickly out of focus, you don't see it, right? So this is why we get always these really pristine images. There are lots of other beautiful things that's more for people doing physics. Imagine you play billiard, you have a whole row of spheres aligned in contact. Something that we also saw is when a particle just hits this row of colloids, you see then a little instability is appearing, and that relaxes away after a moment, and I just have now a nice row on my 2D crystals of new colloids. So just to show you that normally you would expect something else, is we have here another picture where we switch on the bead. We don't have attached colloids, and now you see a pileup of all these colloids, because in this cone of my laser focus, colloids feel a pull, an acceleration towards the center where it is attached. But then you pile up so many colloids so quickly, they just start to push away, and you see that how they are pulling. You don't see even how they are recruited because it's so fast. They hit the interface and then leave it sideways. So there we see the hot spot creates that we have a flow away rather than when it's attached, we have the reverse flow. Now, I know it's very hard to follow up on a talk by Ben, but I hope I showed some nice movies, and that brings me also a little bit towards my conclusions and also some outlook on what we are doing. And so one important thing is we have crystallization that is energy-driven. It's an out-of-equilibrium crystallization, which in itself is quite interesting. This leads to the fact, can we actually use two optical tweezers and see when we switch it on how two crystals grow and how the interface or the grain boundary between them is forming, and can we learn something about this grain boundary dynamics in situ, basically. Another thing that we wanted to do, but unfortunately I moved my lab and I have to rebuild my entire lab now also in Trondheim, and that takes time. But we started playing with large colloids and small colloids. Can we form nice, interesting colloidal crystals with this type of effect? By the way, this is something that you cannot do on a hard surface because very often you get pinning on the surface, and once your colloids are trapped, you can't move them around. So this is why the liquid interface is really important in these experiments. Now, in the meantime, we also looked at different ways of attaching our DNA to these oil droplets, and here I show you a picture where we attached small oil droplets to a very large oil droplet, purely with DNA. So you can play all sorts of tricks. By the way, when I showed you this, you can have mixed DNA, single-stranded DNA on the interface, and therefore also different colloids with the complementary DNA. So you can play directly how many large or small colloids you want to have, because the DNA is so specific that it will only bind those colloids that are that have the DNA, the complementary DNA on that interface. Okay. One thing that we did in collaboration with a postdoc of mine in Cambridge, Chris Ness, who does predominantly simulations, and they're of athermal systems, and we were interested in making, developing sticky emulsions, where we have the DNA is now mobile. You can have different populations and make all sorts of interesting sticky emulsions, and you can do then rheology and see that, imagine you have an emulsion which is eventually liquid and falls apart when you take a drop and place it on a table. But what if you place the droplet and it stays there? And that's only because the DNA holds it in place. And that can be quite interesting also for, I'm dreaming here perhaps, but for drug delivery, where you can inject somewhere some gel or an emulsion and releasing it on demand, different emulsion droplets containing drugs, but you can tune the temperature at which an emulsion droplet comes off as a function of, with the DNA. You can tune that very precisely and sharply. But with this, I want to stop here. This was my group back in Cambridge at that time. Specific thanks are going to Alessio, who did almost all experiments. He was just absolutely wonderful, a brilliant PhD student who unfortunately fell between the cracks and couldn't get a postdoc, even though he was by far one of my best students. Rajesh Singh. He was then postdoc with Ronojoy Artikari, and he did all the calculations, and he developed a little program that is available to everybody. If you want to do ever hydrodynamics, you can run his simulations, which is all based on Python. Ronojoy did a lot of thinking on understanding what is happening. John Hinch helped us with some calculations, but he couldn't solve our problem initially. But it was fun talking to him. With this, I want to thank you for listening, and I hope you enjoyed this talk. And please feel free to ask me questions. Even if you have questions later on, you can send me always an email. Thank you.
Well, thank you very much for the presentation. For one thing, you were amazingly perfectly in time, so that gives space for questions also from the web. So the people watching it via Zoom, again, I urge you, if you have a question, to pose it. But now, I think that we immediately.
Really enjoyed the talk.
Oh, you need a microphone.
Yes.
I said I enjoyed the talk very much, and I can see. I know it's a simplified system. The nanoplastic is very complex, but I can see a lot of opportunities converging towards the nanoplastic sequestration. My question is, most of your studies are spherically symmetric system.
Yes.
What if they are anisotropic? Do you see opportunity to learn new science, or do you think it'll be just a natural extension of isotropy to anisotropy?
Well, if possible, I mean, we worked with FD viruses before also, which were, because they have different DNAs, different code proteins at the end than to the sides, and you can specifically code DNA to different DNAs to both. Imagine in an optical focus, the rods will mostly align in this way and not on a flat on the surface. So you could, in principle, envisage having lots of rod-like molecules forming a little forest on those and do all sorts of interesting things.
And very quick follow-up, I can read the paper perhaps if it is, but have you looked into linker DNA as opposed to direct binding, and whether the length of the MERS make any difference in some of the conclusions?
Well, the link, yeah, you can use linker DNA. We did extensive work on forming bigels, which are double percolating colloidal gels, where we had hard colloids, no oil in there. And yes, you can, we chose this because it was the easiest way, but you can use linker DNA, definitely. You could, in principle, what the group of Miriam Lönissen at NYU is doing, you can use all sorts of linker DNAs that switch, you know, so you have a replacement upon adding yet another linker DNA. So you can play all sorts of these games here on this interface. The beauty of this interface is that it's not stuck to a surface. And that, yeah, because that's the great problem with DNA-coated colloidal crystals. Because of the cooperativity, when you have many linkers at the interface, you get a very sharp melt transition, super sharp. And to anneal something into a crystal takes hours, days, within plus minus 0.5 degrees centigrade. Yeah. So this is why we used also the oil droplets, a liquid interface.
Ben.
My question was also related to make Janus particles, you know, instead of spherical particles.
Yes.
Because we tried it to make propulsion system with Janus particles, and that's not so easy because you have to modify one phase. But can you put something in your droplets? So to make the droplets communicate with each other. So because there's a lot of interest in exchange between droplets these days, no? And information transfer and so on. So I showed you this picture where I had the small oil droplets
linked to the big one.
Yeah.
We had only fluorophore in the small oil droplets initially. And once we had the small droplets attaching, after a while we saw fluorophore inside the big one. Yes, and I mean the long-term goal was to have a droplet fluidic device than a microfluidic device where you can drive your oil droplets, bring them together, let them interact, then separate and bring them to some other station. Yes, yes.
I look around also on the Zoom channel. I don't see any questions there. If there are no more questions in the audience, I should like to thank Erika once again.